Hello, this is a trial. Today I will share a paper called Adaptive Conformal Inference under Distribution Shift. And this paper is published by, I think it's by last year, and it's this one. And it's written by Gibbs and Candace. Yeah. So if you are interested, you can go to see this paper. Okay, so in this video, I will share about the contents of this paper. Okay, so the main abstract of today's presentation, I will talk about introduction first, and also we'll have a quick review about the conformal prediction, and we'll talk about the methods, and we'll comparison to the prior work, and we'll talk about some coverage guarantees, and finally we'll have a real data example and the conclusion. Okay, so the conformal inference is a development method for constructing prediction sets that are guaranteed to contain a target label with high probability. So this guarantee is that if the data are exchangeable, then the prediction set has a valid marginal coverage. That is, the probability of the y belongs to the prediction sets will be 1 minus alpha. So while the exchangeability is a common assumption, so there are many real-world applications in which we do not expect the marginal distribution to be stationary. So for example, in finance and economics market behavior, it can shift drastically in response to new legislation or major world events. So that means it is very common to see the training data or celebration data, the distribution of the training or celebration data are different to the test data, the distribution of the test data. So this paper will develop adaptive conformal inference. This is a method for forming a prediction sets that are robust to changes in the marginal distribution of the data. Okay. So let's have a quick review of the split conformal inference. So suppose we are given a fitted regression model for predicting the value of y from x. So we let y be a candidate of value of yt. So we define a conformity score that measures how well the value y conforms with the prediction of our fitted model. And assume we have a celebration set that is different from the data that was used to fit the regression model. So we're using this celebration set, we define the fitted quantiles of the conformity scores to be the infinity of the sum of the inductive function of SXRYR is larger than P, and we divide it by the number of the celebration data. And then, so if the data of the celebration data and XTYT are exchangeable, and we break ties uniformly at random, then the rank of the SXTYT amongst the points from this will be uniform. So that makes the probability of SXTYT smaller than Q hat 1 minus alpha will be equal to this proportion. And so we define our prediction sets to be C hat, which is y given by xty smaller than Q hat 1 minus alpha. This is given a marginal coverage guarantee of the probability of yt belongs to the prediction set equals to the probability of the SXTYT smaller than Q hat 1 minus alpha. So just a remark, Q is equal to this one. Okay, so for our method, so the next part we'll talk about our methods. So we assume that at each time t we given a fitted score function and corresponding quantile function q hat t. And we define the realized miscoverage rate of the prediction sets. C hat will be denoted as the mt alpha equals to the probability of stxtyt larger than q hat of 1 minus alpha. So this is the probability is over the test point xtyt as well as the data used to feed st and q hat t. So we define the at star. This is the soup of the beta belongs to 0 and 1, which is given by mt beta is smaller or equal to alpha. So if we additionally assume that the probability of the stxtyt equal to q hat t 1 minus alpha t star, this is equal to 0, then we'll have that mt alpha t star is equal to alpha. And so by correctly calibrating the argument to qt hat, we can achieve either approximate or exact marginal coverage. So we use the simple online update to perform the calibration, which is to examine the empirical miscoverage frequency of the previous prediction sets and then decreasing our estimate of alpha t star if the prediction sets were historical undercovering of yt. So we let alpha 1 denote our initial estimated. So in this paper, we will choose alpha 1 equals to alpha. So recursively define a sequence of miscoverage events for ERT. So if ERT equals to 1, then the YT is not belongs to the prediction sets. So the C hat T alpha T is the Y given by ST XTY is smaller or equal to Q hat T alpha T. So we fixing a step size parameter gamma larger than 0. We consider the simple online update. So alpha T plus 1 is equal to alpha T plus the gamma times alpha minus ERT. So we refer this algorithm as adaptive conformal inference, and ERT plays the role of our estimate of the historical miscoverage frequency. So we can see that the choice of the gamma gives the trade-off between the adaptability and stability. So while raising the value of gamma will make the methods more adaptive to observe distribution shifts, it will also induce greater volatility in the value of alpha t. So in practice, large fluctuations in alpha t may be undesirable as it allows the methods to oscillate between outputting small conservative and large anti-conservative prediction sets. So in this paper, it gives an example which is apply the ACI to the prediction of market volatility. So we let a PT to denote the sequence of the daily open price for the stock. And for all t larger or equal to, we define a rate RT and realize the volatility VT is equal to RT squared. So our goal is to use the previously observed returns XT, which is the RS. S is from 1 to t minus 1 to for the prediction sets for YT equal to VT. And we use the Gauge 1-1 model, and this model assumes that RT equals to sigma t and epsilon times epsilon t, and with the epsilon 1 and the epsilon 1 to epsilon capital T is taken to be IID normal distribution of 0 and 1, and the sigma t satisfying the recursive update to this one, to this function. Okay, so And also we feed the model using only the last 1,215 trading days. That is approximating 5 years of market data. And for all times t is larger than 1,215, and we feed the coefficients or gamma. Okay, this is typo. Okay, gamma t, alpha t, and beta t, as well as the sequence of the variance using only the data, the r from t minus 1,250 to t. So the prediction for the realized validity at time t is like this one. Okay, so also we define the conformity scores to be this one. Okay, so this is the conformity score, and the corresponding quantile function will be denoted by here. Okay, and our prediction set at time t will be the c hat equals to v given by this one, and where alpha t is initialized with alpha 1,215. Okay, here's the typo here. Equals to alpha, this is 0.1, and then update recursively. So to measure the performance of these methods across time, we examine their local coverage frequencies defined as the average coverage rate over the most recent 2 years will be this one. Okay, so if the methods perform well, then we expect the local coverage frequency to stay near the target value 1 minus alpha across all time points. So we can see, we can sim this one as the average length in this paper. Okay, so this is the results from this one. So we can see the adaptive conformal is the adaptive conformal is very significant better than this unadaptive, because it is more stable to around 0.9. Okay. So next part we comparison to the prior work. So the first one is Tipshirani showed that the valid prediction sets can be obtained by the reweighting the situation data using the likelihood ratio between P0 and P1, which are the distribution from the situation data and the test point, respectively. And this requires the conditional distribution of y given x to be constant between training and testing, and the likelihood ratio to be either known or very accurately estimated. Okay, so the other one is Caltrace developed methods for forming prediction sets that are valid wherever P1 and P0 are close in F divergence. So if dfp1 given by P0 is smaller than 4, then there exists the conservative value alpha 4 belongs to 0 and 1, such that the m of alpha 4 is equal to the probability of the sxtyt larger than q hat 1 minus alpha 4, which is smaller or equal to alpha. So while I fix the single conservative value alpha 4, our methods aim to estimate the optimal choice of alpha star. And so while then consider only one training and one testing distribution, we work in the fully unlike setting in which the distribution is allowed to shift continuously over time. Okay, so next part I want to talk about is convergent guarantees. So assume throughout that with probability 1 alpha 1 and q hat t is not decreasing with q hat t equals to minus infinity for x smaller than 0, and q hat equals to infinity for all x larger than 1. And so the first lemma is, it talks about with probability 1, we have that for all t belongs to n, the alpha t belongs to minus gamma and 1 plus gamma. So the idea is from the contradiction. So with positive probability alpha t, in such that if the inf of alpha t is smaller than minus gamma, and we note that the sup of alpha t plus 1 minus the alpha t, which is equals to the sup of the gamma times the alpha minus ERT is smaller than gamma. So with the positive probability, we may find the t such that the alpha t smaller than 0 and alpha t plus 1 smaller than alpha t. So we can find if the alpha t is smaller than 0, then the q hat alpha t is equal to infinity, and so that the ERT equals to 0. And we can get the alpha t plus 1 is equal to alpha t plus the gamma times alpha minus ERT. And this one is larger and equal to alpha t, and so this is the contradiction. This is because that the ERT is 0, and also the alpha will be and the alpha and the gamma will be positive, so it will be larger. So we can get this is contradiction because we found that because we know that the alpha t plus 1 is smaller than alpha t. Okay, so this is the lemma 4.1. So from this lemma we can get a proposition of 4.1. So with probability we have that the sum of the ERT divided by the capital T minus alpha will be smaller or equal to the maximum alpha 1 and 1 minus alpha 1 plus the gamma divided by t times gamma. So in particular, the limit of the sum of ERT divided by t is approximated convergence to alpha. So we can find. So we can apply from the lemma. We can apply from the lemma. So we can find the alpha t plus 1 is equal to alpha 1 plus the alpha 1 plus the sum of the gamma times alpha minus ERT. And this one belongs to the interval of the minus gamma and 1 plus gamma. Okay, so the proposition 4.1 makes this is no assumption about the data generating distribution, and it guarantees that our methods give the correct long-term empirical coverage frequency irrespective of the true data generating process, and then approximately tight bound on the worst case behavior immediately after initialization. And we model the data as coming from a hidden Markov model, which can positively show that if alpha 1 is initialized appropriately and the distribution shift is small, then tighter coverage guarantee can be given. Okay, so that AT belongs, so the AT denotes the underlying Markov chain for the environment, and we assume that the conditional on AT and XTYT is an independent sequence with XTYT belongs to the distribution PAT for some collection of distribution PA. So we assume additionally that the estimated quantile function Q hat T and score function ST do not depend T, and we denote them by Q hat and S. So in this setting, alpha T AT forms a Markov chain minus gamma and 1 plus gamma times the A. And we assume that this chain has the unique stationary distribution pi, and that alpha 1 and A1 belongs to the distribution pi. So this implies that the alpha T, AT, and ERT is a stationary process, and thus will greatly simplify our characterization of the behavior of ERT. So this theorem 4.1, we assume that AT has non-zero absolute spectral gap, and we let B and sigma B, and we can get a probability of this one is smaller to this equation. So this theorem, it shows the large deviation bound on the sum of ERT times divided by T minus alpha. And the quality of this concentration inequality will be depend critically on the size of the bias term B and sigma B squared. So the next part, the following theorem shows that if the distribution shift is small, the realized marginal coverage rate MAT alpha T will be close to alpha on average. So this theorem is assumed that there exists a constant L larger than 0, such that for OA and O alpha 1 and alpha 2, then we can get the absolute value of MA alpha 2 minus MA alpha 1 is smaller or equal to L times absolute value of alpha 2 minus alpha 1. And assume additionally that for all A and there is the alpha A star belongs to 0 and 1, such that MA alpha A star equals to alpha. Then we can get this. We can get this equation. So we can see that the right hand of the equation, we can find that we can choose the gamma equals to this one. We'll have the smallest value, and so if we gamma equals to this one, and the equation will become to this. So this is the ideal case of the Q hat. This is the perfect estimated of the quantile of the S XTYT given by AT, and thus will become MAP equals to P and L is equal to 1. So also we can see that the expectation of this one, and this is the quantitative measurement of the distribution shift. So this result can be interpreted as bounding the average difference between the realized and target marginal coverage in terms of the size of the underlying distribution shift. So So also we note that the choice of the gamma equals to this one, it formalizes our intuition that gamma should be chosen to be larger in domains with greater distribution shift, and while not being so large as to cause alpha t to be very volatile. Okay, so we give the real data example. So this example is interesting. It is about the 2020 presidential election. So during the 2020 presidential election, the Washington Post used the conformalized quantile regression to produce the county level prediction of the vote total of the election night. And the YT denotes the number of the votes cast for Joe Biden in the 2020 presidential election in each of the approximated 3,000 counties in the United States. So the XT will include information on the makeup of the county population by the ethnicity, age, sex, median income, and education. So if the order in each vote counts were completed was uniformly random, it will be exchangeable sequence on which we would run standard conformal inference methods. So we apply CQR to predict the county level vote totals. And we consider four different orderings of the counties, each obtained by the sampling counties without replacement with probability proportional to exp the sigma times the county population size. So when the sigma equals to 0, the counting data are exchangeable, and both the non-adaptive and adaptive method perform well. But the sigma increased, the size of the distribution shift increased, and the non-adaptive methods fails to achieve 90% coverage for later counties. And the adaptive methods adjust accordingly and maintains the approximated 90% local coverage rate across all time points. So we can see these four pictures with different of the sigma. So the sigma is equal to 0, and both adaptive and non-adaptive is perform well. But the sigma becomes too larger, and we can see the notes that the sigma equals to infinity. This means the ordering the counties exactly by their population size. So that means the distribution shift will become larger. So the distribution shift become larger. The non-adaptive will become to lower than 90%, but the adaptive one is still maintaining 90%, so it is significantly better than non-adaptive cases. Okay, so this is our real data example. So the conclusion. So the methods in this paper, this is our specific to case where YT is reviewed at each time point. So however, there are many settings in which we receive the response in delayed fashion or in large batches. So also our theoretical results are limited to a single model for the data generating distribution and a special case where the quantile function Q hat is fixed across time. So it will be interesting to determine if similar results can be obtained in settings where Q hat is fit in an online fashion on the most recent data. Also, we choose the gamma based on the size of the distribution shift in the environment. So ideally, we would like to be able to choose gamma adaptively without prior knowledge. So this is our future work. And also we need to determine if our methods can successfully protect against the wider variety of the real-world distribution shift in the future work. Okay, so this is my representation of this paper, and thank you everyone for watching this video, and thank you again, and we will see you next time. Bye.